High in the Peruvian Andes, overlooking the historic city of Cusco, stands a megalithic fortress that defies every rule of ancient construction. Known as Sacsayhuamán, this massive complex is constructed from limestone and diorite blocks, weighing up to a staggering 128 metric tons. Mainstream history tells us these walls were assembled by the Inca civilization in the 15th century using nothing more than stone hammers, bronze chisels, and raw human labor. But when modern structural engineers and materials scientists subjected the seams between these multi-ton blocks to high-resolution 3D laser mapping and petrographic chemical analysis, the standard historical narrative hit a dead end. The stone blocks fit together so seamlessly that not even a single sheet of paper, a thin razor blade, or a human hair can slide between them. The fitting isn't just flat, it is organic, interlocking, and precision curved in 3 dimensions. To appreciate why modern engineering finds Sacsayhuamán so perplexing, you have to look closely at the geometry of the seams. Unlike standard brickwork or European masonry, these stones are not rectangular blocks laid in flat, level courses. They are irregular, multi-angled polygons with up to 12 distinct faces on a single stone. Every single block is custom contoured to match the precise, undulating shape of the stones adjacent to, above, and below it. When researchers ran structural stress simulations using modern AI models to determine how primitive stonemasons could achieve this level of accuracy through trial and error, the computer flagged the process as physically impossible. To fit a 100-ton boulder against another uneven 100-ton boulder using brute force, workers would have had to lift, test, carve, and lower the stone thousands of times. Yet the soft, brittle edges of the limestone show zero sign of chipped corners or impact fractures that such repeated testing would inevitably leave behind. This baffling physical evidence has led material scientists to conduct petrographic and chemical scans on the stone surfaces themselves. Some researchers have discovered microvitrification along the contact surfaces, a glass-like sheen on the rock face that typically forms under extreme heat or chemical alteration. This has given rise to one of the most intriguing hypotheses in modern archaeology. Were the stones somehow softened at the joint using unknown chemical compounds or thermal technology before being pressed together? Local indigenous folklore recorded by early Spanish chroniclers describes a forgotten plant extract capable of dissolving solid rock into a soft, clay-like consistency. While mainstream geologists argue that the smooth fit was achieved purely through hyperpatient grinding with river cobbles, chemical testing of the microscopic residue inside the seams continues to spark intense debate in material science labs. The architectural engineering of Sacsayhuamán serves a purpose far beyond simple aesthetics. It is an anti-seismic masterwork. The Peruvian Andes sit directly on major fault lines, subject to devastating megathrust earthquakes that have repeatedly flattened modern brick and concrete structures over the centuries. Yet, the zigzagging, interlocking walls of Sacsayhuamán have stood completely undisturbed for hundreds of years. The secret lies in their mortarless, modular design. During a massive earthquake, the unmortared, multi-angled blocks don't crack. They literally dance and flex in place, dissipating shockwaves through the joints before settling back into their exact original positions. The builders didn't fight gravity and seismic force, they mathematically calculated how to use fluid geometry to absorb kinetic energy. The transportation of these gargantuan stones presents an equally daunting engineering puzzle. The largest limestone megaliths were quarried in Rumacolca, over 35 kilometers away across mountainous terrain, deep ravines, and river valleys. Moving a single 120-ton stone over uneven terrain without steel cables, heavy machinery, or paved roads would require the simultaneous effort of thousands of workers pulling in absolute unison. Yet, the narrow mountain passes surrounding Cusco show no physical trace of the massive engineered causeways that would be mandatory to move such dense weight without sinking into the soft mountain earth. The sheer logistics hint at a level of spatial planning and mass organization that rivals modern industrial supply chains. Today, Sacsayhuamán remains one of the most imposing physical riddles on planet Earth. As white-gloved researchers, materials scientists, and AI models continue to analyze the microscopic contact points between these ancient multi-ton giants, one reality becomes perfectly clear. Whether built through decades of unimaginable human labor or a lost scientific understanding of mineral behavior, the individuals who carved the walls of Sacsayhuamán possessed a mastery over stone that modern tools still struggle to replicate, leaving behind a 100-ton riddle written in solid rock.